Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. If you've made it this far in differential calculus, you have made it almost to the end. We are now on the downhill slide, is what I like to tell my students. This is where you start learning about Calc 2. So you've just finished talking about limits and derivatives and how to apply those derivatives. Those are the three major topics you've gone through so far. And now you're about to enter into this vague weirdness called integrals or integration. Before we get there, we have to have a minor discussion about something called an antiderivative. And this will be very nice. It fits very nice and snugly between differentiation and integration. So this is a wonderful topic to really get a hold of, and actually it's pretty understandable. So let's start here with just the concept and basic theory of what an antiderivative actually is. A function, and we usually denote that function capital F, is called an antiderivative of a function little f on an interval I if the derivative of capital F is equal to little f for all x on that I. So normally we would say if I have a little function f here, its derivative would become f prime, right? But we've never really talked about what happens if you go the other way instead of graduating down to the derivative. And I always think of the derivative as going down a level on a ladder, if you will, because you're, I don't know why, actually. I really have no clue why I think of it that way, but just visually for me, I always think of it this way. You have this ladder. Let me draw a ladder here. You have this ladder, and you're currently at this rung called function f. One derivative down is f prime. Two derivatives down is f double prime, and so on and so forth. But we've never talked about climbing the ladder. We've just talked about going down this ladder. Also, something to note, each time you go down a rung on this ladder, you could lose information. It's sort of like each generation that goes by, you kind of dilute that generation, whatever that means, right? So when I say you lose information, for example, if the domain of f was all real numbers, it could be the fact that the domain of f prime might be all real numbers except for 1. And the domain of f double prime might be all real numbers except for 1 and 2. So each step of the way, every time you take a derivative, you might lose some information. That's one way to think about this. But like I said, we never really talked about how do you climb this ladder? How do you get to the thing you took the derivative of to get f? And what we're calling that right now is capital F. That's what you would take the derivative of to get to little f. That is capital F prime, which I'll write here. Capital F, its derivative, capital F prime, is equal to little f, just like the derivative of little f is equal to little f prime. Anyway, that's the antiderivative. The antiderivative is going the other way. Rather than taking a derivative, you're doing the antiderivative. I guess I think of it this way as well, like subtraction. So if you're at the number 10, you would subtract a level to get to the number 9, and you would subtract a level to get to the number 8, and so on and so forth. And anti-differentiation is like addition. You would add a level to get to the number 11, and you would add a level to get to the number 12, and so on and so forth. I don't know if that makes sense to you, but that's always how I've looked at it since I was a student. So if the antiderivative is the function you would take the derivative of to arrive at your little function f, let's go ahead and find the antiderivatives of these functions right here. So every time you're handed a function, in this case, part A is the function little f of x is equal to e to the x, you should ask yourself, what would I take the derivative of to arrive at e to the x? And I've written that instruction off to the side because I'm going to be using that quite a bit. Well, I hope you understand you would take the derivative of e to the x to arrive at e to the x. And that's because the derivative of that function, capital F, is actually just e to the x. So the antiderivative, or I should say an antiderivative of e to the x is e to the x. It's one of the easiest functions to work with. Well, what about cosine of x? So part B. And notice I renamed the function there. It's little g of x is equal to the cosine of x. So I'll call its antiderivative capital G of x. So let me zoom in and just do that. Capital G of x is its antiderivative. And we just ask ourselves the question, what would we take the derivative of to arrive at this function cosine of x? Well, if you think sine of x, you're slightly wrong. You would actually not take the derivative of, well, actually, yes, you would take the derivative, sorry. You'd take the derivative of the sine of x to arrive at the cosine of x. I was trying to be cute there and have a negative, but never mind, don't worry about it. So you would take the derivative of the sine of x to arrive at the cosine of x. And again, that's because capital G prime of x, I'm laughing at myself right now, is equal to the cosine of x. You do have to watch out for negatives because had I written the function, let's suppose we had the function little k of x is equal to the sine of x. That's what I should have had as an example, just because it's a little more interesting. Then its antiderivative, what you would take the derivative of to arrive at that sine of x, is actually a negative cosine of x. So there's a little more thought process in finding antiderivatives because you have to remember the derivative of the cosine is not the sine, it is actually the negative sign. So you need to worry about that negative. So, and this is again, capital K of x is the antiderivative because capital K prime of x is the opposite of that negative sine of x, right? So let me do it this way. It's a negative, and then the derivative of the cosine is a negative sine of x. And so therefore, negative sine is a positive sine. All right. So you do have to watch out for little tricks like that. The last one there is one of the most important functions to deal with when it comes to antiderivatives. So part C, we have a function, little h of x is equal to 1 over 1 plus x squared. And again, you would ask yourself, what would you take the derivative of to arrive at this function? Let me put that over here. What would you take the derivative of to arrive at this function? Well, think about all the derivatives or all the functions you know the derivatives of, because that's all you can do. There's no other hope you have. You can't just make up some random function. And you will find that the one function whose derivative is 1 over 1 plus x squared is the arctangent, or the tangent inverse, however you want to call it. So the arctangent of x, again, that's because the derivative of that capital H, which is arctangent, is 1 over 1 plus x squared. There's something to think about here. Differentiation is pretty straightforward. Now that we've gone through it, you should be able to somewhat agree with me. When you take derivatives, unless it's a chain rule or something like that, it's pretty straightforward. Just a derivative of a function is pretty easy to do. But antiderivatives, not so much. Antiderivatives are actually a complete mess. And the reason for that is mainly because we don't have any really good methods to take antiderivatives. Well, we have some, but you have an entire course dedicated to it, and that's Calc 2. All right, so here's a theorem. If f is an antiderivative of a function, little f, that is, if capital F prime is equal to little f on some interval, then the most general antiderivative of little f on that interval is capital F of x plus c, where c is an arbitrary constant. Now, before we go to prove this, let's just see why this is true. Let's go back to one of the examples that we just did. So notice in this question, I didn't say state the antiderivative, I said state an antiderivative. And that's because of this specific theorem that we're about to deal with. Think about it this way. If I handed you the function not e to the x, but what if I gave you capital F of x is equal to e to the x plus some constant c? Well, its derivative would be e to the x, and then the derivative of a constant is 0. So the derivative of that capital F is actually equal to still little f. So therefore, that capital F, this guy right here, is an antiderivative of little f. And it's the most general antiderivative because you have this general arbitrary constant represented there as well. So it could be any e to the x plus any constant that you want. The proof uses a theorem that we have worked with in the past, and I mentioned in the video when I presented that theorem that this was the gateway to Calc 2. So I'm going to, off to the right hand side, just write down kind of the crux of that theorem. If you have two differentiable functions on an interval and their derivatives are the same on that interval, then those functions must just differ by a constant. That's what that theorem had said. And we use that, I think, to prove trig identities and stuff like that. It's a really cool way to do that. So that's what we're going to do here. I'm just going to say, let's go ahead. We'll start with if f is an antiderivative of little f on I. So we'll start with that. There we go. Capital F is an antiderivative of little f on an interval I. That's the antecedent for this theorem. And we want to prove the consequent, right? Then the most general antiderivative is just capital F of x plus c. What we're going to do is just allow a function g to also be an antiderivative. So suppose that capital G of x is another antiderivative. Well, then by definition, capital F prime and capital G prime both equal little f of x. So therefore, capital F prime must equal capital G prime. And by the theorem that we had proven in a previous lecture, if two derivatives are equal, or two functions have derivatives that are equal in an interval, then those two functions must just differ by a constant. So thus, g of x must equal capital F of x plus some c, where c is an arbitrary constant. Since g was just some random other antiderivative, this means that any other antiderivative is of the form f of x plus c. And that's what I wrote here. Since g was representative of any other antiderivative of little f, all antiderivatives of little f have the form capital F of x plus c. And therefore we have proven that the most general antiderivative of little f is capital F of x plus c, because any antiderivative of f of little f of x can be represented by capital F of x plus c. QED. All right, let's go ahead and use this. And in general, by the way, when somebody says state the antiderivative, they really truthfully mean the general antiderivative. So when you're talking antiderivatives, you definitely want to have that plus c in that conversation. So part A, and I chose each of these for a very specific reason. Part A, we have f of x is equal to secant squared. Again, we're just asking ourselves a very simple question. What would you take the derivative of to arrive at this function? Well, we know we would take the derivative of the tangent to arrive at this function. So I'll just say that capital F of x is equal to the tangent of x. But now we're going to put in a plus c because that would be the most general antiderivative. Again, because anytime you take the derivative of this capital F, it'll be secant squared plus 0, or just secant squared. So usually, like I said, when students first encounter antidifferentiation, which is actually a word, they get very happy because at first they're intimidated, but then they realize, oh, I'm just undoing the stuff that I've been doing the entire time. That's exactly true. You do have to watch out for some of the more obscure derivatives that you took before. So let's talk about this one right here. G of x is equal to 1 over x. This is one of the most important derivatives in all of calculus, and its antiderivative is one of the most important antiderivatives in calculus. When we covered the derivative of what becomes 1 over x, we made a little mention in the theorem that we have not used up to this point, but we're going to use it now. Now, I'm actually going to go ahead and paste in my what would you take the derivative of to arrive at this function. I'll paste that in, and I will go ahead and start to say capital G of x is equal to, and most students would say the natural log of x, and then plus c, but you're actually wrong when you say that. Here's the page from the lecture that I did on that topic, the derivative of the natural logarithmic function. The derivative of the natural log of the absolute value of x is equal to 1 over x. Now, if x was strictly positive, it still holds. The derivative of the natural log of regular old x is still 1 over x. However, if somebody said, hey, I've got this function 1 over x, what did I take the derivative of to arrive at that? It is not the natural log of x, it is actually the natural log of the absolute value of x. Be very careful about that because that's critical in calculus 2. So why we were wrong is because we need to take the natural log of the absolute value of x plus c. So that's the antiderivative of 1 over x. It is very important that you know that. At this point, you've got to start practicing that. It's easy to forget, I know, but I harp on it a lot because it becomes critical as we move forward. Finally, let's take a look at that little h of x, which is x to the negative third, because I haven't really done any polynomial work, so why not? So little h of x is equal to x to the negative third power. And again, we just ask ourselves that question we've been asking all along. What would we take the derivative of to arrive at this function? And you, of course, if you took the derivative of something, when you take its derivative, you lower its power by 1. So obviously this, the function we took the derivative of, must have had a negative 2 power, because when you take the derivative of something with a negative 2 power and you end up lowering its power by 1, it becomes the negative third power. But if you were to take the derivative of this capital H as written, it would be negative 2 x to the negative third, which is not what little h was. So we need to offset that negative 2. So we'll have a multiplication of 1 over a negative 2. Again, that's to offset the fact that we didn't have a negative 2 out in front of that x to the negative third. So the antiderivative of x to the negative third is negative 1/2 x to the negative 2. That's a multiplication sign between those. I was just trying to be fancy there. You could double check your work. H prime of x is equal to a negative 1/2 times, and let's see, we bring down the negative 2, x to the negative 3. The negative 2 cancels with a negative 1/2, and you get x to the negative 3. So it does work out. In general, just letting you know, we're not going to actually write it down as a theorem until later, but it is kind of nice to write out right now. I'll just write it in blue, and I'll write it as a theorem anyway. The antiderivative of f of x, which is equal to x to the nth power, where n is not equal to negative 1, because we know that if it were equal to negative 1, it would be the previous problem. It'd be that g of x, which is 1 over x. So the antiderivative of little f of x, which is equal to x to the n, where n is not negative 1, is going to be capital F of x, where we added 1 to the power and divided by that new power. That is actually the opposite of differentiation. In differentiation, you subtract 1 from the power, and you take that old power and multiply the function by it. So this is the opposite of that. You add 1 to the new power, to the power, and divide everything by that new power. So that is a theorem that could be proved later on. We'll not worry about it right now. So as far as basics, this covers the basics of antiderivatives. In the next video, we're going to go into finding the antiderivatives of sums and differences of functions, which actually is as easy as it should be, to be very honest with you.
It's It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.